Okay, let's get started. All right, so we're going to talk about this. I'm not in a very good condition right now, so will be a little bit light compared to others. So let's think about first review what we talked about last time. Basically, we have a 3D point in the 3D space, um, x, y, z, and want to express that what's the relationship of that point, 3D point, and the 2D projected point on the image P. Okay, and the way you express this is that you first express that point from the wall coordinate system in terms of x, y, z, and you said that there's a translation between the wall and the camera, right? Because the camera could be in different places, right? So tx, ty, tz, so you can use that translation to model the difference between the world and the camera, okay? It can also have the rotation, right? It can also basically every two coordinate system, they are related by a translation and rotations. So this means that you can take the xyz1, that's a coordinate of the of a 3D point in the wall coordinate system, and then the first step is to multiply the RT with the xy1 xyz1. This is basically says that I want to express this coordinate in terms of this coordinate. Okay, from this coordinate to this coordinate, right? That's what the first matrix multiplication is trying to do, right? Once you express the same point here in the camera coordinate system, you can project them onto the camera. And we talk about the projection itself is this simple matrix, okay? You can project it onto a single camera. And once you are the coordinate, this vector is on the camera space, then you can you can resize it and then shift the locations depending on the focal length and the U naught V naught. Okay, so from the camera to the image. Yes. We say it again. We don't know, of course. Like this is the whole process. Basically says that if I tell you what the rotation and translations and the focal length and U naught V naught, then I would know exactly how the relationship is from the 3D point to a camera from an image. Yeah, yeah, yeah. Since can you say that again? Sorry, I didn't get it. Focal length is the distance from the center projections to the center. Yeah, exactly. Will be able to find where that XYZ point will land on the image plane. Which is the big P on the left side. The T basically initially because the XYZ is expressed in the wall coordinate system. But if I want to do the projection, I need to first compensate the coordinates difference. I want to basically express the same point if original XYZ is expressed by the coordinate wall coordinate theorem. But I want to re-express the same point in the view of this coordinate system. I need to do the coordinate transformations. And the coordinate transformation is represented by this RT, rotation and translation. So the point doesn't change. It's just a different way to like just the reference frame is different. For example, this lamp right now is one step ahead of me, but the same lamp could be like one step and this step ahead of me, right? So it's just a point of view difference. Okay. So once you have this, so you basically this is the whole process. You have a 3D point in the wall coordinate system. You map them to camera and then project them onto the this use the projection matrix, and then you have the camera to image coordinate transformation, right? So all of this it's great that you can model all this in linear transformation. Okay, and typically you for convenience you can merge these two together so that you have this RNT. You basically drop the last row. So people call it intrinsic and extrinsic metrics. So what intrinsic means is that it's specific to the camera, intrinsically to the camera itself. Extrinsic basically says that it could be because when you change the wall coordinate system, it will be changing, right? So it's extrinsic to the camera. Okay. All right. So if you this is the most important part because everything in module 3 come from here, right? Come from this K, the intrinsic and extrinsic transformation, and we will be able to derive everything from this camera linear camera model. All right. Any questions about this part? All right. So this is a projective model, but if you think the object is far away, or your focal length is actually very large, then you can use a simplified projection matrix that's called weak perspective model. It's basically just whatever image is 3D world in this 3D space, you just directly project them onto the image. Okay, so it doesn't have the perspective shortening effects. So here are some examples that people use. Basically, the parallel lines will remain parallel in this kind of projections. Okay, this is called orthographic projections. All right, so and last time we talked about the concept of depth of field, but we didn't give you visuals. So here are some visual kind of example to show you that because last time we talked about if you use a kind of barrier, you have this trade-off between want to get more light or more light, but you get blur results and less light or sharp result. You have this kind of trade-off, right? So here that's why you introduce a lens in between at the center of projections so that lens can bend light so they can gather light and focus that light onto the one point at the image plane. So this shows that if you and then you can control. This gives rise to the concept of depth of field, right? So basically, because the lens can only focus on a content that's on the specific locations. So this is basically where the object is in focus, and anything after that will be out of focus. Okay, so the range here that's stay in focus is called depth of field. Okay, so in this case, because you have a large aperture, so you bend more light onto the image, so you have a shallow depth of field. Basically, if you deviate from the depth focus plane, the object will quickly become blurred. Okay, so you get something like this. Okay, so you get something that's the background become like people call it bokeh. Yes, deviate from the plane that's in focus. Okay, so in this case, it's this object here. And last time we talked about you can actually compute where that plane is by computing like the distance to the image sensor. And yeah, and once we have this, you could, but here this is a trade-off you're making, right? So you gather more light, so you have a better, more light, higher SNR, signal to noise ratio. But at the same time, you have to live with this. You can only you can only put a particular depth plan in focus and you have shallow depth of field. So to control the trade-off, you can also bring back the idea of a pinhole camera where you have an aperture. So you can see that now you break out more light. You can see that you have a more depth of field. You have a larger depth of field. Okay. Of course, this is a trade-off. because when you reduce your aperture size, then you let less light in, right? And which means that you have a lower PSNR, which means that if you want to capture the same quality of the image, you have to set your exposure longer, right, to get the same amount of light. Okay, so this is all. If you are into photography, these is all the kind of different trade-off you're making. Okay. All right, so some more examples. If you kind of change the aperture, in this case, is if a large aperture, so you can see that only the front chair is sharp, and all the chairs behind it is become blur. And if a small aperture, you can see that everything is sharp. Okay. Um, and so it seems that if I want to capture images that's just as sharp as possible, the sharpest image that we can have, maybe we can just keep decreasing the aperture. All right, just make the hole smaller and smaller and smaller. Okay, so but that's not the case. Like, can anyone tell me why we cannot just keep shrinking the hole, the aperture, so that we get sharper and sharper image? Yes. Yeah, that's one reason that there will be less and less light coming to the hole. But there's another reason that you probably learned in high school physics. What happened when you have a light that passes through a sinkhole? Yes.
Does it like get smaller as possible? Like it looks like it's going further away.
So we always think about light as a kind of a particle, right? So they follow a line. But when you have a hole that's small, what happened? Any? Yeah, it becomes more like a wave, right? Because there's a dual property. So when you have uh, uh, thin hole, like very tiny hole, what happened is that you will get like two problems. One is the less light will come in, and the second problem is that you'll have diffractions. The light comes into, like, remember the physics experiments you may be doing, where the light pass through the tiny hole, you will have this wave property. And so this is what happened when you decrease the kind of the focal, the aperture size. Initially get sharper and sharper results, but gradually still get deteriorate. Okay, so this is a fundamental physics that we cannot get infinitely sharp images. Okay.
For
Yes.
that live blurring on post, when you change the focus on the camera, the blurry on, you twist it all the way to the left, blurry, and you twist it all the way to the right. It's also
Right. When you change I think you're referring to the focus ring on the DSLR. It's not the same thing. So when you change that, it's changing it's scanning through the focus plan. It's changing. It's changing this plan. Okay. It's changing this plan. Basically where the object is sharp. Okay. Right. And then you can have I think in this area you can have some dial that can change the aperture, but you can get smaller and smaller. Too small, you're still not getting any sharper. Okay, so that's the fundamental limit. All right, something also related to the camera is the concept of field of view. Basically, it's the range. That's basically this is the sensor, and this is the range. Field of view usually expressed in terms of degree. Basically, how many degrees you can see from these things. Okay, so you can, from simple geometry, you can factor find that it's related to this one because the tangent of a field of view is like 2 tangent of this guy is equal to d divided by the 2f, right? So there's some kind of simple applications, right? So if you see that if you have a larger sensor, like if you're a DSLR camera, if I have a larger sensor, you naturally have a larger field of view. Okay, that's why kind of in the DSLR, people want to use full frame sensor that have a larger sensor size, basically larger B, which means that you see a larger field of view. Okay, and if you change the focal length, if you increase the focal length, what does it mean? Like in this case, if your focal length is large, then you have a smaller field of view. So this is good for example, you are capturing a sports photography. So you can actually, your field of view is very narrow. So you can see all the kind of players in the very distant regions. Okay. All right. So one thing people can play around with is called dolly zoom. Basically, the idea is that if you capture an object and you change the field of view, for example, you increase the focal length, at the same time you get back up. Because when you change the field of view, if you change the focal length, the object should become larger. But at the same time, if you go take a step back and to make sure that the object size remain the same, then you have this kind of interesting effects. Okay, so this has been done in the movies a lot. So here are some examples. So basically zooming from a Boolean way. So people have been playing around with in the movie industry. All right, so I also use this in my own research as well. So if you just take a single image and if you estimate the depth map, basically for every pixel you guess uh, where the how far away this pixel is, and then because of that you know every pixel in 3D. So with that you can change the dolly zoom effects by changing the focal length while moving backward. Okay, so you can get results like get effects like this. You know, so you can create visuals like this. All right, so all of this about cameras. So now we know about sufficient amount of camera. But if I give you an image, how do I know this K and R? Okay, so this goes back to kind of pretty much that it seems that throughout the lecture we only have one tool to solve every problem. So this and here is no different. Okay, so now let's say you have x relationship between the 2D point x small x and 3D point x big X, and you have some unknowns here, right? So you don't know the intrinsic of the camera, you don't know where the camera is, the extrinsic. Okay, so how are we going to calibrate? This is the idea of the process of recovering the numbers in K and R and T is called calibration. Okay, I need to calibrate the camera so I know what exactly the parameters of this camera is. Okay. So the first idea is very simple. I can try to, if I have a 3D object, let's say that is grid here, and I have some dots, like a salient point on the grid. And because I made this, I can make this this plans. So I know exactly what the measurements are in kind of physical measurements of these points. So what I'll do here is this for every location, from this graph, if you run your um, um, Harris corner detections, you will be able to detect each point very well because it's very salient. So you can detect all the corners well. And now you have for each point you have a 2D point, 2D locations. And then you also know their 3D locations because you know these points are from something that you made in 3D. Okay, so you know the 3D point and you know the 2D coordinates, you can estimate it. So the question is, how are we going to solve for the for these ends? Any idea? It seems that it's one tool, right? So we also use the same tool. Okay, so what we will do is that these are unknown variables, and the way we solve anything that's related to this, this is, by the way, this method is called direct linear transformations. So what we do is that we just first write it out as a linear system of equations. For example, what we'll do is that we will write this out into a bunch of equations, okay? A bunch of equations like this. And you can organize this equation so that it becomes zeros, like this. All right, so it's expanding all the equations here, but now there are some values that are known, right? The x is known and small u and v are known as well, okay? So what you can do next is to right. What you can do next is basically move the unknowns into a column vectors and all the others as coefficients. Okay, so you can set up the linear system equation either as a form of ax equals b or as a form as ax equals 0. Okay. Okay, so there are two options here for you to solve this. Okay, so method one is a borrowing. So you can set up this and remember that we will use the because these m's you have some constraint, right? These m's is not arbitrary, right? Because when you map this xyz point onto this string, these points are in homogeneous coordinates, which means that it could be scaled by arbitrary s, like any scaling s is the same. To convert that homogeneous coordinate to the actual coordinate, we'll divide it by the last item. Like make sure that it's 1, then you get a UV back. Okay. But when you do this, which means that these values are up to scale, right? So you don't know the scale of this, right? So what you do here is that you basically put all the unknowns into a big vector, and all these remaining parts of this are just put it in the big matrix. Then you have the form of ax equal to 0. But obviously this m is not all 0, right? But if you just look at this m, if you just put the n as 7 all 0, then a 0 vector is 0, right? Then you automatically satisfy. But that's a trivial solution that you want to avoid. The reason why it's trivial is that these guys, you don't know the scale. So one simple choice is to impose a particular scale. For example, I can impose that the norm, the L2 norm of these vectors is 1. Okay. So if we impose that scale, then you know how to solve it, right? So this is the same way we solve for the for the equation earlier. Right? So you have ax equal b equals 0. So the way you solve this is to apply a SVE on this matrix, and you pick the eigenvector that corresponds to the minimal eigenvalues. Okay, pick the vector such that you multiply by this, only the smallest eigenvalues come out. Okay, so this is the kind of pseudocode of this. Okay. Any questions about this?
I'm still confused with the top part. Like, when you get those two equations, like, I understand the the
Right.
first half of what you added together, but the second you subtracted on something.
Okay, so it's come from here. Sorry, it comes from here. Like this equation is like if you multiply this first row and this xyz, it's this guy. And the second row, if you multiply this guy and this guy, is this guy. Okay, so because you have you multiply by this guy and you got SU and multiply this guy is SV, and if you multiply this guy is S. So you can shift it around. I guess I missed some steps in terms in the algebra here. So you multiply this guy equals to SU, but all right. So you multiply this vector and this vector, you get something you get something on this part, right? And you can multiply this guy and this guy, it is something in this part, okay? But this part is equal to SU, right? So initially this should be SU, but what is S? The S is this bar minus this vector multiplied by this vector. Does it make sense? Yeah. So left hand side is this guy times u, or they can see that this guy is this guy times u and this guy times v. Okay. Yeah. So some simple algebra you get, and then you can move this around to get a linear system equations. Once you get the linear system equations, you pull out the unknowns into a column vectors, and then something that's known is as a matrix of coefficients. Then you can solve this. Like either you pass it into the solve with SVD, or you can just assume that the last one is 1. This guy is 1, and then solve the remaining part. Okay, so either way will work. Okay, so with this, you just solve pseudo inverse, kind of least square solutions. Yes. So basically, with this, we are able to get all the coefficients. But what we really want is the K and the R and T, right? So and then there are some methods that can try to factorize this big matrix M back to KRT. Okay, I don't want to go into too much detail because it's very elaborated kind of approach, but just let you know that once you this is where the calibration comes in, like where you have if you have an image, single image capturing a known object, and if you know the coordinates of all these objects points in 3D, you can use the linear system equation to recover the n. And then because this K is the upper triangle matrix and rotation is orthogonal matrix, and T is just a 3x1 matrix, 3x1 vector. So with that, because you can use this property and recover to have a decompositions from N to KRT. Okay, so this is a simple method with calibration, but it doesn't work in real world. So what you really will want is that can I take a picture, maybe a building, then I can automatically recover what's the focal length of that picture. Okay, so if you are able to recover the vanishing points, then you can do that. Okay, so here's a second method that that can do that. Okay, a vanishing point is basically a convergence and intersections of all the parallel lines in 3D. Okay, so all these parallel lines in 3D. In the 3D world, they don't converge, right? Because that's what parallel means, right? All these points, all these lines are parallel, so they don't converge on in the real world, but they converge on the on the camera, okay, from the image plane. So you can see that these lines converge onto this part, this line converge to this part, and this part maybe converge on infinite. Okay, so if you have an image that has three orthogonal vanishing points, like up like this one, you have a three orthogonal vanishing points, and you can use that and it's three orthogonal vanishing points, and then you can estimate the location of the on all these vanishing points in the image, and from there you actually can recover the intrinsic. Okay, so here's what you can do, right? So what we know is that these vanishing points are xi, but these vanishing points, because these are the points that are infinite. So which means that the last item, the xyz1, the last item is 0. All right, so you don't have the translation. You don't need to worry about the translation. So any point that's projected from the vanishing point to the camera, pi is just krt xi, right? Which means that you can express this xi as the r inverse k inverse pi. So, and this is where the orthogonality comes in. I know that these 3 points in the 3 vanishing points, each pair of them, they are orthogonal, like from this direction and from that direction. And if I have 2 vectors that are orthogonal, what's the mathematical relationship between them? If I have 2 vectors that are orthogonal, yes. The broad product becomes 0. So exactly. So what we will do is that we use this for any ij like mention point 1 and mention point 2, point 2 and point 3, and point 1 and point 3. They have this constraint. Okay, so you have this constraint, and what you do is that you apply this constraint. So if you plug in this xi and xj, plug in this constraint, you get 3 equations here. Okay, so here's more details what you could do. Okay, so again, you have a vanishing point in 3D and you have a vanishing point detected in 2D. What you do is that you plug in these three equations, and because you have a rotation here and rotation here, this actually can cancel out. So you have for any xy location of the vanishing points, you have these equations, 3 equations. Okay. So then you have a bunch of algebra things. Yes. Yep. So vanishing points are if you have parallel lines in 3D, and all these parallel lines will converge onto like they won't converge on the physical space, right? That's why they're parallel. But if you have a camera to look at these parallel lines, those parallel lines will converge onto a point. And that point is called vanishing points, just like this. Okay, so any parallel lines in 3D will converge onto the same variable. Yes.
How does the camera know that those lines are parallel?
How does the camera knows those lines are parallel? So you can design algorithm to do this, right? So you can design so you can design, like, for example, the algorithm will look like this. So you take the image and you run candy edge detection, and you run the run the segments, run candy edge, and then feed kind of run half transform to get the lines, and then you can have some hypothesis like which one is the by sampling two line segments, you get a vanishing point hypothesis. And for that, you can vote, right? See which one is has most inliers. And that's why you can get potential, that's how vanishing points are detected automatically.
They figured this out like 100 years ago. Or this is
No, like algorithm-wise, it's not like algorithm-wise, it's probably after the ransack. Like ransack, once you have ransack, you can deal with this very robustly.
Oh.
But vanishing point has been kind of this perspective concept has been around for century, kind of like 5 centuries probably. Okay, that's how, when you're drawing any type of architectures, you'll need these kind of tools. All right, so once this is you can go through the algebra. It's kind of a bit boring, but basically just want to show you that it can be done. Once you have this, you can just expand the equations, and then you can figure this out. Okay, you can solve this. Right, so in the end, it's basically just like based on the vanishing points, and you can figure out the U naught V naught. Okay. Once you get a K, you can also figure out orientation of the camera with respect to the world. Okay, so the reason why you can do this is that you have this KR XI. You can set the coordinate of the 3 vanishing points as this, right? 1, 0, 0, 1, 0, 1, 0, and 0, 0, 1. Okay, just basically set the coordinate system of the X, Y, Z in the world coordinate system. And now, if you took this R of this, right? So this R is 3 columns, 3 columns of this, right? So what it does is that any P1 is basically just take the first column of the rotation matrix, and the second column is take the second column and third column. And then you use the property of the rotation matrix. That is, each row has unit length, and then they are orthogonal to each other. Okay. Then you can solve this. All right. So that's how you can use the vanishing point to calibrate your camera. Like you can recover what are extrinsic parameters and extrinsic parameters. So I want to kind of get us focused on more on how you can use vanishing point to measure the height of a 3D object. Okay, so if you look at this image, if you may wonder like from this image, you can anyone guess like what's the height of these 2 people? Are they roughly the same, or one is higher than the other? Any idea? Okay, so they're probably similar, right? Probably similar height. Okay, but if you just do some image processing, like you crop out that the second person and the back, and put it in front, you get something like this, like very weird, right? The image space, the distance of the height distance, for 2 people are very different. But somehow you get a completely different, somehow you can correct this. This is because you're using the perspective cubes. Okay, so here's how it works, right? So if you look at these things, like you can see that this from this I show the vanishing lines, like all these lines that are converging to the same thing. And this you use the fact that vanishing point, the lines that converge on the vanishing point, they are lines that are parallel in 3D. What does it mean for 2 lines that are parallel? It means that every point, the distance remains the same. Okay? So what it means is that in this case, you can clearly see that these 3 guys, this guy is highest, like tallest, and second, and so on. So you can see that they are different height. But what if I have the camera capturing this, but it's here? Now they should have the same height in this case, right? The reason they have, that they have the same height is that because these lines they are parallel in 3D. Okay, so here's another example. All these objects should be the same. Okay, so we use this a lot in our daily life to kind of so that you don't so that even if the image size is very different, but because you use a perspective cues, you can make sense of the objects. Okay. So your brain can correct those object size. So you have to understand what the object size is. But it can actually also fool you to demonstrate, this is a good illusion to demonstrate that your brain is making sense of the image that you see. Okay, so here's an example. This is called Amy's room. Basically, it's an illusion where these two people that they found a twin here. They sit in the same room. This is not digital process, right? This is the exact physical space, and the two people are in this room. But because this room is oriented in a way to fool you, from this viewpoint, you see that the grid all kind of, they look like perfectly normal, but now you see that the person has a very different size. Okay, so this room has this structure. By the way, there's a room in the Baltimore. Sorry, it's in Baltimore. It's called Marion Science Museum. They also have this room. So if you are interested in, you can check it out. So you can actually see this example that like this is the image. So it's kind of look people. You may feel that you can make this up, but it's actually
Well, I
works
did.
for videos.
And now I can. At the Exploratorium, San Francisco's Science Museum. How did I do it? The easy way. I'm manipulating your perception.
Okay, so which means that you're making sense. Every time you're because you are assuming this object, this space is regular. All right, so you're using these perspective cues but you can actually, but it's actually very different. Okay, so you have this kind of interpretations. But in normal life, normal everyday life, you can use this to actually, from a single image, you actually can measure the height of a person or objects. Okay, so here is how you can do it. Okay, so you have a compare different objects. Okay, what you know is that if you can connect the bottom of these objects, and then you connect the bottom of the object and you find the vanishing points, then you connect these lines, they should be the same height. Okay, because vanishing point is all the lines that are parallel to each other in physical world. So all these lines, these two lines are parallel with each other, which means that they are the same height in physical space. All right, so now you can use this fact to do things. Okay, so imagine I have something that's some reference in the physical space. Okay, I have some reference in the physical space. How do I measure the height of this person? Now, if I know the ground plane, basically the intersection of these two vanishing points, what I'll do is that I will first draw the ruler of the bottom of this one, connect this ruler with the objects, and then connect this, and now I get a vanishing points, right? Vanishing point here, and this vanishing point, I connect this vanishing point with the height of the person, with the top of the person, you get this guy. Okay, so now you can read exactly what the physical height of this, and you can do this with a single image. You don't need like 3D or the thing. Simply by knowing that the vanishing points are the convergence of parallel lines. So you can do the other things. For example, you have a turtle here. You can also do the same thing, like increase these lines, and then to get this one. Okay, so there could be very useful applications for example, every time you see some kind of crime scene, right? So some kind of CCTV's security footage of some suspect, right? So I probably see that a lot. From the single image, actually can use this cue to estimate what's the height of a person, right? By looking at the surrounding, by looking at the vanishing points and looking at surrounding. For example, if I know exactly, if I take a picture of me and this table, and if I know the table height, I will be able to guess what my height is. Okay, by compensating these perspective cues. Okay. All right. So, but what if you don't have this reference, the direct ruler? How do you do this? Okay. So what you will do is the following. So you have a reference. You have a reference point. You have a bottom of objects and top of objects. So the height is what you want. Height is what you want, and you have some reference points. Right. You have this ratio that you want to. If you need to know, you want to be able to know the ratio here. Okay. So the interesting about perspective is that perspective cues is that there's some quantity that's invariant to no matter where the camera is. Okay. So this is called sync cross ratio. This is called cross ratio. That's basically, let me see if I show. Okay, this quantity. If I have a line, I have 4 points. I have a line of 4 points, and this ratio, that's basically the distance between P1 and P3 and the P2 and P4 divided by P3 and P2 and multiplied by the P1 and P4. This ratio is some constant. It doesn't matter how you view these 4 points. Okay. So we call this projective invariant. And with this invariance, you can do some very interesting things, right? For example, in this case, we have 4 points in the physical space, right? So you have this cross ratio in physical space. So this ratio is the same as H and R. And at the same time, you have a camera look at these 4 points, right? Look at these 4 points again. So this 4 points project into T, R, B, and vanishing point of the up, right? Vanishing points. So this ratio should be the same. Okay, you can use the image cross ratio, and this guy is the same. So with this, we were able to recover the height of the objects. Okay, so how do you do this? So it looks like the following. Okay, imagine that your objects is there's some reference here, and you want to measure the height of the persons. Okay, measure the height of persons. So what you do is that you draw this line between the bottom of the reference and the bottom of this guy and intersect with the ground plane. And then now you have this, you can draw a line here to get a T. So now this is H, this is H, and this is R. The ratio between the and at the same time you compute the image cross ratio. You have an image cross ratio, and it will be the same as H divided by R. Okay, and with that you can recover the actual results. Okay, so I'm going to show you a video that shows you how exactly this can be done. How you can apply this cross ratio to measure something that you don't have direct measurements. Okay, so I think this is it's a very long video. I want to see if I can skip something. But I think the story is really
I've been thinking about the World Cup a lot, Brady. And then I was reminded of this really incredible goal that just turned a little bit over 20 years old. And it was a goal that Roberto Carlos from the Brazil national team scored on France in preparation for the World Cup 20 years ago. One of the most incredible goals in history. It was a free kick that didn't seem like it was very dangerous. You know, he needs to take a shot from really, really far away, and he had this incredible ability with free kicks. It went like it was just going way out of bounds, and then it curled at the last moment and went inside. Players can usually do this with the inside of the foot, but to do it with the outside of the foot and have it curl that much is something that I had never seen, and I don't think anybody else had before.
I do it quite a bit.
Yeah?
Yeah, I'm pretty good at that.
We're gonna have to see on the pitch later. I was looking at old footage, and there were all these articles celebrating the goal, and I was noticing a discrepancy. These articles didn't agree on how far he was from the goal. So some articles talked about how he was 35 meters away. Others talked about how he was 35 yards away. That's not the same thing. And then it got me thinking, how do we figure out how, you know, nowadays we watch these games and they automatically tell us how far the ball is, but how do we figure that out? And I found that it's a lot harder than I thought. And so I wanted to talk to you about how we can do this, and looking at this still of the photograph of Roberto Carlos's goal, I want us to just look at this and figure out how far he was. So this is Roberto Carlos. Then the end goal is a little bit hard to see, but it's right here. So the goalkeeper Fabian Barthe is standing in front of it. This right here is the edge of the penalty box. And then this one is sometimes called the goal box or the goal area. The point is that we basically want to figure out, okay, you know, here are these three lines, and here's the ball. And with that information, how do we determine how far the ball is from the end line? Maybe I will try to draw a picture of the box. Can't do this and not put the penalty kick out over there, although we can't use it. It's basically from here to the end line. And here there's some things that are worth pointing out. One thing that I find fascinating about soccer fields is that they're not all the same size, but the boxes are always the same size. And I hope you'll forgive me that I'm going to do it in metric system, because those are the numbers that I'm used to. So in Spanish, we call the little box la 5,50, because this is 5.5 meters. And sometimes in Spanish, we call this one la 16,50. La 16,50, because that's how long it is, 16 meters and a half. What we want to do is somehow figure out how to go from this picture to this picture. And right away, we see an obstacle, which is that the wall is in the way. And so we actually don't know how to draw this green line because the wall is blocking where, you know, the reference points. And so the only thing that we're able to do is draw a diagonal line. It's as if we were going to kick the ball, and we actually need to avoid the wall and draw a diagonal that will go from where the ball is sitting to, I don't know, somewhere. Precisely the issue is that because this is a photograph, it distorts angles. When we have a right angle here, that's not a right angle in the picture. And so we actually don't really know exactly where the 90-degree will be. Here's one thing that we might try to do. We might try to say, okay, since we have to draw a skew line over here, then we should probably draw it over here also. So let me draw it over here. And I think that the first thing that I would try to do is I might say, okay, well, if this distance right here, 16.5, and then this distance right here is what I'm trying to find. Let's call it x. Of course, if I know x, then the distance from the end line would be x plus 16.5. Then I think one thing that might be worth doing is seeing how these distances transfer to this red line. So if I draw this line right here and this line right here, it feels like they should be related. Actually, one thing that is true is that 16.5 divided by x is equal to this distance divided by this distance. I think it's worth actually drawing a little picture here to keep that in mind. So let me go ahead and do that. This is you could use that equation to solve x, except it doesn't. And why doesn't it make sense? Because there's a change in perspective. Because here, in this picture, I'm looking at the field from on top, whereas here, I'm looking at it from the front. And when I do that,
the ratio becomes different.
If I look at it in this way, it's like when you walk in a room that has a square grid of tiles, and the ones that are closer to you look bigger than the ones that are farther from you, even though they're the same size. And so we have the same issue here, that this part over here actually looks bigger than it really is. And so what we need to figure out is how does a change of perspective change measurements? And this is an interesting thing, because this is a very, very classical problem in geometry. And it was first developed when artists and geometers were trying to figure out how to draw in perspective. And it's a little piece of geometry that has been somewhat forgotten, actually. I think we should talk about it. We have a green line and a red line. And then the question is, if I'm standing right here, how do the distances in the green line transfer to distances on the red line? So if I try to draw a picture like the one that I drew back here, except now the lines are not parallel, they meet at a point. Okay. Then the question is, how does this distance and this distance relate to this distance and this distance? And the trouble is, they don't. There's no relationship between them. No matter what two distances you choose here, you can choose a place to put this line so that you can get any other two distances here. There's no relation between these two numbers and these two numbers. And what the classical geometers figured out is that you actually need an additional line. So we're going to introduce an additional line. Made it very close. What they figured out is that now if you look at this number over here, so if I call this distance A, this distance B, and this distance C, and I call this little distance A, and this distance B, and this distance C, then the question is, how are these related? It turns out that the answer is this beautifully mysterious thing, where if you take 4 points, like these 4 points, maybe I'll call these points A, B, C, and D, then there's something called the cross ratio. What you do is that you compute the distance AC, you compute the distance BD, you multiply them, and then you divide by the distance BC and the distance AD. I think this is a totally weird thing to do. That's the cross ratio. Why do we do this? Because it turns out that this is the quantity that is preserved by a change of perspective. So if I compute this quantity on my red points, I'm going to get the same answer as if I compute that quantity on my green point. You can imagine, for example, one way of thinking about this is that if I look at this picture, you might think that this is a projector and this is a wall. And so if you're trying to project a movie and you angle the projector differently, then you're distorting the picture in the wall. And as you know, some things become bigger, some things become smaller. And the question is, what doesn't change? And it turns out that the one thing that doesn't change is the cross ratio. It's a very strange thing. But that's the thing that is going to allow us to compute Roberto Carlos's goal, because this is just a change of perspective between the angle of the camera and the angle from the sky. And so we can just compute the cross ratio in these two pictures and get that it should be fixed, and we'll figure out the distance. One thing you might notice, we don't have enough information now, because to compute the cross ratio, we need 4 points. And here, when we were looking at these lines, at the green line that we're trying to compute, we were only paying attention to where Roberto Carlos is, and this point, and this point. We're missing a 4th point. Okay? Now, luckily, the soccer field have the 5 con 50 box, the goal box, and so we're going to use this point right here. This 16.5 meters splits up into 5.5 here, or 6 yards, and 11 here.
Skip the they compute this. Okay, see.
And so now this distance over here was 4.5. And so now we should figure out how much is this and how much is this. Now, I can make a wrong guess. The wrong guess is that, in the real picture, this is twice this. And so I might guess, oh, then this would be twice this. It should be 3 and 1.5. But we talked about how in this picture, these distances look longer if they're closer to you. So I think when I measure this, I should get that this should be bigger than 2 times this. There's our distortion there. So let's take out the ruler and measure it. 1.3. And so as I just did,
let's see.
3.2 plus 7.3, that's about 10.5. And divide by the small distance in the middle, which is 3.2, times the big distance, which is 11.8. So this is the cross ratio in the photo, 1.251. Let's do it maybe to 3 digits. And so that's what I can measure. That's in the photo. That's the measured cross ratio. Now, what is the real cross ratio? Let's compute it over here. So first, I'm supposed to take the distance from here to here, right? Now that's 5.5c plus 11c, so that's going to be 16.5c. Now I'm supposed to compute this distance, 11c plus xc, so I'll factor out the c, and I'll get 11 plus x times c. And now I'm supposed to divide this by the small distance in the middle, which is 11c, and this big distance, which is 16.5c plus xc. And again, I'll factor out the c. Now, one lovely thing that happens here is that all the c's cancel out, right? This cancels out with this cancels out with this, and so we just get something in terms of x. This is the measured cross ratio, this is the real cross ratio, and then the magic here is that these two numbers are actually equal to each other. So this is equal to this. 181.5 plus 16.5x is equal to 181.5 plus 11x times
All right,
1.2.
We'll skip the algebra part. But basically, what you could do is, in the end, is like this.
All right.
So that's how far he is from the box.
So that's how far he is from the box, exactly. So x is equal to approximately 16.63, which if you look at it, is actually pretty much the size of the box, right? So the box is 16.5, and he's 16.6 away. So he's basically 2 boxes away from the goal line. And then if we add this, so that's it. That's how you do this.
Not bad. Good go.
It's pretty cool, no? I really thought this was a lot easier. I actually.
All right, so I think this I really like this because it's really demonstrating that how kind of like cross ratio will be used to solve real world problems, even from a single image, by leveraging the fact that you have some measurements along the way, and by making use of the cross ratio that's projective invariance, which means that you can measure the physical distance relationship with the image-based relationship. And this has been used a lot in the single image metrology, right? Basically, you can measure height and distance from a single image by using the perspective cubes. Okay, so to sum up, basically what we talk about in this lectures is that we talk about vanishing points are the on the intersections of parallel lines in 3D. And then we also talk about the pinhole camera models, kind of how you represent a 3D point in the world coordinate system to a 2D point in a camera. Okay, and starting next lecture, we are starting to talk about 2 cameras. All right, so we'll talk about what if I have 2 images and how are they related to each other. Right, so first we'll talk about what if you have a rotating cameras, and what will happen in that case, right? What's the relationship? And then what if you have a translation camera, like 2 cameras that translate to each other? And then we'll talk about multiple cameras and so on, okay? So that's about that's what we'll cover in module 3, right? Any questions so far? Okay, if not, I'll get around 8 minutes back. Thanks.